Section 4.4, logarithmic equations and functions. We're going to be determining the domain of a log function, the x and y intercepts of log functions, graphing them, solving log equations, and solving applications of log functions. So the first thing we're doing is finding domains. Domains are the values for which the argument of a logarithm is a positive number. We can't take the logarithm of a negative number or of 0. The argument is what we call the expression inside the log, what we're taking the log of. So x squared plus 1 is the argument, 1 half x plus 1 is the argument, x over x plus 1 is the argument. So in number 1, I've already taken the argument x squared plus 1 and set it greater than 0, because it can't be 0 and it can't be negative. Well, I move the negative over and I get a negative 1. It doesn't matter what number we plug in for x, when we square it, it becomes a positive number. And every positive number is going to be greater than negative 1. So guess what? This particular problem is always true. And what that means is that the x values that we can plug in are anything. We can plug in any numbers from negative infinity to positive infinity. The next one, we're going to take the argument 1 half x plus 1 is greater than 0. We don't even need to worry about this one at all. That does not affect the domain. That is only affecting the range, and the range is already all real numbers. That's just moving our graph up 1, but it's still going to be all real numbers. So we're just talking about the domain. We're just setting the argument greater than 0. So we have 1 half x is greater than negative 1. Solving it, we get x is greater than negative 2. All I did was multiply both sides by 2 to get rid of the 1 half. So negative 1 times 2 is a negative 2. This is the way we can actually write our domain. That is in what we call set notation. If we'd rather, we can write it in interval notation, which would look like this. A parenthesis meaning it's not included, a negative 2, and then an infinity meaning it goes forever after that. Okay, we're actually not going to do part 3 if you've been looking at the notes on your own. This is solving a rational inequality, which is in chapter 3, which we skipped. We're actually going to do a little bit of chapter 3 starting in the next week or 2, but we probably will not do rational inequalities. So if any of you want to explore this on your own, again, it's in chapter 3, and I think I have most of the textbook in Canvas. So there's a few of you that are juniors that if you're going on to calculus, you might want to look at that, or let me know if you'd like some individual help. Okay, moving on, we're going to do example 2. We're going to sketch the graph of this function that we saw in example 1. This was our second problem right here. So let's go ahead and find the domain, which we already did in the last problem. We found out it was negative 2 to infinity. Let's find the x and y intercepts. So found the domain, find the x and y intercepts. So if you've forgotten how to find the x and y intercepts, we need to set y equal to 0 and solve, and then we're going to set x equal to 0 and plug that in and solve. Okay, so for our x-intercepts, we set y equal to 0. So this is y, f of x equals 0. So I really don't have room on this page to do all of this. I should have given you more space. Obviously, this was a failure in planning well for space. So I'm just going to get me a whole new page here, and then we can look at both pages at the same time. Okay, so x-intercepts. We will set our equation log base 2. Oh, it's log base 3, my bad. Of 1 half x plus 1 plus 1. We're going to set that equal to 0. We're going to move the 1 to the other side. So we have 1 half x plus 1 equals negative 1. Then we're going to change this to exponential form. So 3 to the negative 1 power equals 1 half x plus 1. Well, 3 to the negative 1 power is the same as 1/3. So that gives us 1/3 equals 1 half x plus 1. I'm going to subtract the 1 from both sides, so I've got to get a common denominator to subtract it. So that would be subtracting 3 over 3 in order to subtract that 1. So subtracting 1 is what that step was. So I changed that to 3 over 3. And we get negative 2/3 equals 1 half x. So now in order to get rid of the 1/2, we multiply by 2. So that gives us -4/3 equals x. So there's our x-intercept at -4/3. All right, to find the y-intercept, we're going to set x equal to 0. We just need to plug that in. So let's go with our function. Y equals log base 3, 1/2. We're going to plug 0 in for x, plus 1, and then plus 1. Okay. So this turns into 0. So we're doing log base 3 of 1 plus 1. Well, log base 3 of 1 is 0 because 3 to the 0 power is 1. And 1 plus 0 plus 1 is 1. So our y-intercept is at 1. All right, next, step 3, we're going to use transformations. Something, I don't know if we've dealt with problems this complicated before, but we can actually factor out, when we're figuring out our transformations, we can factor out. So we have log base 3, factor out the 1/2. That means if we take 1 and we divide by 1/2, 1 divided by 1/2 is 2. It's a reciprocal. So the reason we do that process and take that 1/2 out like that is because 1/2 gives us the compression of our graph, and this plus 2 means it's going left 2, and this plus 1 means up 1. So left 2, up 1, and it will have a compression, right? All right, we can plug in other points if we want to have other points to help us with our graph. So if we want to plug in x values, we can get y values. So for example, if I were to plug in 4, the reason I chose 4 is I do half of 4 and I get 2, and 2 plus 1 is 3, and the log base 3 of 3 is just 1. So then 1 plus 1 is 2. So there's another point in our graph. Because this is moving up or left 2 and our asymptote is normally at 0, that means our asymptote is going to be at x equals -2. And that's because of that 2 right there. Okay, let's go ahead and throw this all in and sketch it. So we have an x-intercept at -4/3. That's about right there. And we have a y-intercept at 1. And we have an asymptote, vertical asymptote at -2. My computer changed what I was doing. Okay, now let's plug in the other point we found, which was at 4, 2. So over 4, up 2. And our graph is going to look approximately like this. The entire graph should have moved up 1, left 2, and it should be compressed. We didn't really write that in there. We kind of ran out of room. So this has a vertical compression of 1/2 because of the 1/2 that we factored out. All right, that is example 2, a little complicated. Section 4.4 is kind of a pain. 4.5 is better because it's more practical applications. All right, this one has an absolute value in it. We can go through the whole process the same way we just did, but I'm really not going to worry about this one. So I would like you to just skip example 3. If you want to look at it, it is on the notes that I posted from my Math 1050 class in the fall. The next thing we're going to be doing is solving log equations, and I'm going to make a separate video for that.